Hello and welcome to our video for Unit 2, Forces. Let's get started. So in this unit, the main thing that we covered is the definition of a force and how we can express that mathematically, right? We know the sum of all the forces in a system is going to be represented by the mass of all the objects in the system times the acceleration of the system that you're choosing. And the important part to remember is this formula is very versatile because you can actually choose what system you're going to be looking at. If you're looking at a pulley with two attached masses, you can choose just the masses, each of them themselves, or you can choose the whole string, the whole pulley connecting both masses and treat that whole quantity as a system. It's just that when you change these parameters, you're just going to be modifying the M and the A accordingly. In addition, you're going to be the judge of how the motion is chosen to be. If you have a pulley and the left mass is going downwards, you can say that all the forces positive are going downwards, or you can say that all the forces going upwards are positive. In the end, it really comes down to just how you look at your system. If you really goes the wrong direction, you're just going to have a bunch of negatives, right? And they'll eventually cancel out to get you the right answer. And finally, remember that force is always in newtons, or kilograms times meters per second squared. It's not just meters per second squared or just kilograms, right? It has to be them multiplied together because it equals MA. Right. So on this slide, we have a few questions, and we want you to take a second to pause the video and try to figure these out if you haven't already, and we'll be going over it very shortly. So number one, when we take F left and set it equal to F right, what necessary condition allows us to do so? Right. So when you're thinking here, if I can say that the forces pointing to the left is equal to the forces pointing to the right, then what conclusion are we going to draw about the system? Right. Well, first of all, we know that the force of a system is the force left minus force right. Right. So if we can set them equal, that means that force left minus force right is equal to 0. Because essentially what we're doing is we're just changing the equation of F left minus F right is equal to 0. We add F right to both sides, and we end up getting F left equals F right. So if the total force on the system is going to be 0, that means that there's effectively no acceleration, meaning that it's going to be moving at constant velocity or just not moving at all. And number two, when we analyze a system of masses, will examining at each object individually be the same as looking at the whole system together? Well, and the related sub-question is, does the choice of system affect how many forces we need to observe, right? Now here, you want to kind of think about trying to solve a problem in many different ways, right? Well, one way you could solve a problem that has many different masses, you could look at each one separately and just calculate the force equation for every single object. Or instead, you could look at the whole system together and just calculate the whole system's acceleration, the whole system's mass, and get those equations that way. Well, it turns out that it doesn't really matter. As we saw in the previous slide, the only big factor is just whether you're talking about a system or just a bunch of different objects. In the end, the only thing that's changing is that, right? Essentially, the accelerations in masses, they'll all be relevant to that one system that you're talking about. So it's honestly just your choice. But in my opinion, it's usually easier to look at the whole system, right? Because that means that you can cancel out all the little forces in between everything. So if you're looking at three objects and they're each connected by strings to each other, right? Object 1 is connected to object 2, object 2 is connected to object 3. Instead of looking at each block individually, if you decide to look at the whole system, you can just cancel out all the tensions in the strings that connect each object to each other, right? You can essentially ignore that. And that makes everything a lot easier in general. So that kind of determines the internal and external forces, like what they truly are, right? External forces are the ones outside a system pulling on it. There's no Newton's third law pair to cancel that out, essentially. And we'll get into that more in a bit. But final question, does friction point against the net acceleration of the object? So usually when the problem says that friction is not negligible, it means you have to consider it, right? And in most cases, or in all cases, I should say, the object will always have some feature, some quantity relevant to the friction. The friction's gotta point in some direction that's logical to the object's motion, right? So, but there's a common misconception that friction, because it's a force, it's just gonna be in the opposite direction of the object's acceleration, right? Because acceleration is related to force. But actually that is completely wrong. In Although this is not really going to change anything in most cases, sometimes you need to know this fact. That friction points against actually the net velocity of the object, essentially the relative motion between the object and the surface. So just because an object is accelerating doesn't mean friction points backward. Sometimes the object could be moving backwards but then accelerating forwards. And in that case, friction does point forward, the same direction as the acceleration, believe it or not. So just be careful when you're dealing with problems that ask for friction, because you're going to know how to get the direction correctly. Now let's talk about friction and springs, two other extremely interesting and important topics that might just show up on any problem in general. And friction is going to be the more common of these two, right? In almost every object in real life, you're going to see friction when you're rubbing a book along a table, or you're trying to push a box along the ground, along the floor. Right? And it's important to note that when we're talking about friction, theoretically, friction occurs in two stages. So we have static friction, and then later, when the object is in motion, it becomes kinetic friction. So that's why in some problems you might see that friction, they give you two coefficients. They give you the coefficient of static friction and also the coefficient of kinetic friction. The thing with static friction is it only occurs when the object is at rest, right? It's not accelerating, it's not in motion, none of that. It's just at rest. That's why it's called static. And the thing with static friction is it's quite dynamic. So if it's going to be very volatile, it's going to be able to adjust to all the forces that's pointing against it, right? If you're trying to pull a box, it doesn't move until a certain threshold, right? And that threshold, as you can see in this graph here, is that peak when the static frictional force is equal to mu s times the normal force of the object. And when it reaches that threshold, meaning if you don't apply that much of a force, it's always going to be balancing it out. Static friction will always balance your force out, always prevent the object from moving unless you apply a force that's greater than mu s times n. So once it reaches that threshold, as you can see in the graph, it drops and is relatively constant. In fact, that's what we know as kinetic friction. That's when the object is in motion, and it's kind of like the friction between the molecules doesn't even want to try any longer, right? It's already tried its hardest to oppose all the forces we put on it. Now that it's in motion, it's only going to be constant. It's going to be following mu k times n. So it won't, once your object is in motion, you can easily find the frictional force. It's always going to be mu k times n. I'm going to follow that formula. Obviously, as we've seen, static friction is a little bit different because static friction is going to balance out your forces for you. It's going to take care of that until it exceeds the threshold, right? So those are two important differences to note between these two forces. And again, remember that friction always points relative opposite of the relative motion of the object in question between the object and the surface that it's on. And another force to be aware about is the spring force. If you ever get a question where it's asking for the force on a spring, right, you're going to have to know the relationship. And it's simply that when you have a spring and it's not in equilibrium, meaning you're either pulling it a certain distance from its resting lane, it's going to actually exert a force back onto itself. It's going to exert it in the opposite direction. So if you have a spring and you're pulling it to the right, so it's being pulled, the force is going to act to the left. It's almost like friction, just a little different, because its direction depends on the displacement from equilibrium, if it's going to the left or the right from equilibrium, right? So, and the formula itself is relatively easy to handle. It's just going to be F is equal to K times X, and K is a constant, and usually the problem will give you what K is equal to. And the units for K is going to be newtons over meter, simply by that force relationship. So springs in general are relatively easy if you were talking about horizontal springs, but in the case of vertical springs, you'll need to do a little more digging with the accounting for all the forces, right? Because you also have gravitational force when you're looking at a vertical spring. All right. All right. Thank you so much for your support and for watching our video today. If you have any questions, make sure to reach out to us on Remind. Our code is PHYSIHS, BIZIHS, and we'll be sure to cover it in future meetings. Regardless, thank you again. Have a great rest of your day, and make sure to subscribe and like our video. Thank you.